doing mainly the atlas of moon, as well as some chemical as well as geological mapping. So we were quite successful in reaching that orbit, and essentially we also had a a kind of sudden flare. I would call it a rage, because this moon impact probe is the one which was sent along with that, and then it created a sensation, saying that water molecules were present in the on the moon surface, and this was also endorsed by NASA's moon mineralogy mapper. So with that, we got a good impetus for this particular mission, and then lunar program took off. But of course, we had some real delay because of technologies which need to be developed if we need to do further on moon, like landing. So essentially, Chandrayaan-2 program was slightly offset. It was not immediately preferred because of ISRO's other commitments for remote sensing and communication, as well as navigation satellites to be realized within the time frame, and also the technology gap which we had for that lunar program. With all these delays, eventually this Chandrayaan-2 could be realized during July 2019, and this was done with the the first GSLV Mark 3 version, which we call presently as LVM-3 vehicle. And with the experience of Chandrayaan-1, we could easily maneuver this particular spacecraft to reach its trajectory on August 14th, 2019. And then we could successfully induct the orbiter into the designated orbit, and then we could do some orbiter related scientific payload studies. However, the intention was to have one more landing that time, and then we also had this one more important payload, which I'll show in the next slide, called this orbiter high resolution camera, along with the terrain mapping camera, which for which optics has been developed at this LEOS lab and supplied to SAC for final assembly and integration. This proved to be of great help because it could get a mapping in about 2 orbits with a resolution of around 0.32 meters at 100 kilometers through that orbiter. And then we had a field of view, and then within 2 orbits we could decide on about a strip of around 0.5 by 0.5 kilometers on the moon, where the lander has to soft land. Of course, we also developed this digital elevation model to do this and all. It was in a primitive stage at that time. And of course, as is well known to this community, we had a lot of glitches in the landing. Of course, it was missed by a whisker because of the major glitch in the software, our NGC. Though others were also having some gaps, but major glitch happened in the software. So it could not be a successful landing that time. But eventually, the learnings what we had with Chandrayaan-2 really helped us. For example, this OHRC camera could completely map the moon within this stipulated time what we had for Chandrayaan-3. And these are the slides which show about how we have generated the DEM during this Chandrayaan-2 landing phase. So we passed on to this Chandrayaan-3. Of course, we were struck by this intermediate pandemic related issue. Fortunately, it helped us also to have some more tests to be carried out. And idea is this time we should definitely have a safe and soft landing on the moon. So objectives were more or less similar, but we had plenty of technology improvements, which we have learned from Chandrayaan-2, and also we developed some newer technologies. For instance, there is one velocity sensor called Laser Doppler Velocimeter, so which was inducted newly into this mission, and each and every sensor as well as scientific instruments were better calibrated. And then essentially that designated site also, we enhanced that strip to 4 kilometer by around 2.4 kilometer strip instead of a 0.5 by 0.5. and we had a very clear mapping of that particular strip, which was in the North Pole. And then the rover also, we had extensive tests done at our lunar terrain test facility at ISITE. So with all this, what I would want to say is like this robustness is the one which has really helped in the success of Chandrayaan-3. Everywhere we have done extensive and very elaborate tests to improve every system performance, every subsystem you take, whether it is sensors, propulsions or anything. Even NGC, a lot of things have been improved upon, and also we kept redundancies for every of this sensor as well as other devices which were flown along with this. Since time given for us was extensively high, plenty of simulations also could be done. We didn't just stop with the hardware in loop tests or software in loop. Even OBC was kept in loop and then tested at several locations. And there were some short circuiting tests which were done in Chandrayaan-2, which were overcome in Chandrayaan-3. For example, this integrated cold tests, which was done with the helicopters, plenty of learnings have happened where our sensors could not give an update, how we have to correct, what kind of wrong updates also have come, how to eliminate them. So these were the learnings both in ICT as well as IHT. IHT is another very important thing where we almost, from 60-meter descent down to touchdown. So this is very, very important to, do everything in loop. So this was done in real time and then ensured that with all the sensors in the loop, we are definitely sure about landing. So in essence, the Chandrayaan-3 configuration had very similar ones like what we had for Chandrayaan-2, the propulsion module, the lander which is called Vikram, as well as this rover known as Pragyan. Only thing is there were certain modifications in terms of engine configuration. We dispensed with that central engine of 800 newtons. The thruster, only four engines were 400 newtons capacity were kept. And also this 56 Newton thrusters, 8 numbers were retained. And we had an improvement in our test down sensor also. So we have done a lander drop test and then ensured that, any leg touches, we should have a cutoff of the engine from that. And also later it was improved that unless 2 leg touches, we should not, stop the engine. So as I told earlier, we had this heritage of this our GSLV vehicle, which is now termed as LVM-3. So this is the 4th generation in that version. The first one was used for Chandrayaan-2. After then we had 2 successful launches with that same launch vehicle, and then Chandrayaan-3 was the 4th one. So in a sense, this has got a capacity of nearly 4.5 tons to lift the payload up to geosynchronous transfer orbit. And this Chandrayaan-3 mass was typically less than, very closer to around 4 tons. And this was launched on 14th July 2023 from Sriharikota, Shar. So as is intended that it went into this, geosynchronous transfer orbit of 36,500. It's a highly elliptical orbit with the perigee being at 170. And then we had this AOP of around 178 degree with an orbit inclination of roughly 21.4 degrees. So this was quite successful, and there are absolutely no glitch in that launch. Then followed by this, we started making our maneuvers. So essentially we had about nearly 6 earthbound maneuvers, out of which 4 were done in perigee positions, 1 in apogee, and 1 is a translunar injection. So this was all quite successful. And then this is where one very important sensor of LEOS called star sensor. This comes into loop to update that inertial navigation sensor to keep the spacecraft intact in its particular orbit. So this is a very useful development what we have done, and then that led to this, reaching that lunar orbit very safely. And then once it was injected into lunar orbit, we had this other lunar bound maneuvers, wherein 5 numbers, which includes this lunar orbit insertion as well. and followed by that we had this separation of this lander from the propulsion module. This time we didn't call it as orbiter. It is a propulsion module. It was intended in the event that we could not do these maneuvers properly. Still, we have a window of taking it further. So essentially, this propulsion module has been left with plenty of fuel that it can run for almost a decade now. So of course it has got only one payload called SHAPE, which was supposed to do some spectropolarimetric studies of habitable planet Earth. That is why it is called SHAPE. So that is doing its job now in the propulsion module. And of course this lander once having separated, we have taken it for 2 deboost maneuvers to bring it to a conducive elliptical orbit. And we were waiting for every system to be intact to go ahead with the final landing phase. So these were the 2 deorbit maneuvers which were done and the orbits which we have attained. And you can see here just before that how that separation has happened between the propulsion and the lander module. And the most important crucial phase is this power descent phase. So this is partitioned into 4 parts. Okay, one is that rough braking phase, other one is the attitude hold phase, and the fine braking phase, followed by the final descent, terminal descent phase. So very important here is just before the start of rough braking, we need to take an update with our star sensor to clearly know where that for that orbit determination we need to have that update, and that is the one which will be compared after final landing where we have really landed. So this became very smooth. We got the update, and then we started killing the velocity. Vertical velocity was almost 0 in the rough braking phase, and then it was traveling at a velocity of 1.68 kilometers per second. And then we got the updates sequentially, which I will show in the next slide with all the type of sensors what we had. And then in the attitude hold phase, velocity reduction has appropriately happened, both in horizontal as well as vertical, where we need to give some negative acceleration to kill further speed of this particular one. And then we went through this fine braking phase where really velocity has to become 0. And eventually reach a phase where the entire spacecraft will be now 90 degree from where it was orbiting in the other lunar orbits, and then we have put it successfully vertically, and then seen that at about nearly 800 meters height, it has to do a hovering to see whether the landing space is hazard free. So that is where some special sensors also will come into picture. And if not, one more chance we have at 150-meter height, wherein one more study will be made. Yes, we can go ahead with landing, or else we can retarget. There is a time stipulated for that of around 22 seconds. In the first hovering we have 12. In the second hovering we can do a retargeting. So wherein our sensors processing time has to be reduced and say that okay, we can do a retarget and go to a different place. I forgot to mention one more thing, that even just before landing also we had one more one landing site as well as one alternate landing site. In the event that things were not conducive or orbit determination could not be done properly, then we can postpone that landing by another 3 days. So essentially this graph captures how we have maneuvered and then did this landing in a very successful manner. Those are it is simulation. Yeah, of course it's a real-time update, but what happens is like that is the numbers are actuals measured from this one and then given that.
There are some secret numbers and all, it should not be revealed.
No, nothing like that. In this there is absolutely no secret and all. Like what technology aspects what we kept is that has got its this one. As otherwise it is the numbers are real-time numbers only. Yeah. So these were the set of sensors which were used for landing. For the navigation, guidance and control system, these 2 sensors, inertial and absolute sensors, are the ones which aided in this. And inertial sensor we had only one, that is called LIRAP, that Laser Gyro Based Inertial Reference and Accelerometer package, which was done by IASU, and this can work up to touchdown. That's how the beauty of this particular one. Touchdown. This can give update up to touchdown. And then in the absolute sensor category, these absolute sensors are very essential because inertial sensors drift will be there. So this is what gets, the absolute sensors update will keep it, in the right, frame. So in the absolute sensor category, we had this microstar sensor, which is very important for all this, reaching up to this orbit, as well as these altimeters, velocimeters, then hazard avoidance sensors, as well as the final touchdown sensor. And each one you can see that how it has got its own redundancy. Altimeters, we had a laser altimeter and a carband altimeter. Of course, the ones which are shown in dark blue is developed by LEOS, and carband radio altimeter was done by SAC. And in velocimeter, we have developed this laser Doppler velocimeter for the first time using fiber optic based technology. And also this lander horizontal velocity camera, which we developed earlier, we made a significant improvement in terms of its rate capability as well. So this LHVC camera proved to be very crucial. I'll come back to that a little later. And then lander hazard avoidance camera also was very crucial. When it came down to around 150 meters, it has ensured that there is no hazard in that particular strip and then landing space, and then it went on smooth. So this is the sequence of how this sensors update happened. As I explained to you that that OD was determined with the star sensor mainly, and then this happened at 30 kilometers, and then followed by this Kara and LASA update, carband altimeter as well as laser altimeter. This was in attitude hold phase at 7 kilometers, and the velocity update with LDV happened, but there was a small glitch there. I'll explain a bit later. This happened fine breaking, though we had some 2-channel update. The 3rd channel there was a glitch. And then we also had this backup, this one from LHVC at a hovering time. This is the main sensor which is used, and Kara and LASA used to give continuous updates. And then at 150 meters, LHDAC was on, and then it has taken the pictures, and vertical descent was facilitated under these particular conditions, and we had update from all the sensor till touchdown. So the first one which was done by IASU, I have just captured some of these particular specification parameters. What is more important here, this is the inertial navigation sensor which has aided from the beginning till end, and this comprises of a ring laser gyro and an accelerometer put together, that is called LIRAP, and it measures the angle as well as our acceleration parameters. So the delta V is arrived at from that acceleration only, and it has it has got 4 sensors, one being an hot redundant for that, kept in a tetrahedral, as you can see here. The 3rd or 4th one is behind this, and then we had this electronics package separately kept. So this there is a higher rate capability for this type of LIRAP. It can go up to 30 degrees, whereas fiber optics gyros are limited by the rate basically. So they can go only 1/3 of this value or even lesser than that. And also the bias stability is reasonably good, though in other gyros we get better, but this is enough for this particular purpose. And these are the other parameters which are meant for this accelerometer channel. And what they have used is a CSAP based accelerometer, and then this inertial navigation till touchdown, we have seen that performance. It was really good that this important sensor has given a proper update at an appropriate time and then aided in safe landing. And also we had this option that during deboost phase, this can also lead to engine cutoff. That is one major important event which we have to decide in the deboost phase. And microstar sensor is what we have developed at LEOS, and this is the sensor mainly used in both the propulsion as well as the lander modules. This is essentially a 3-axis lost in space absolute attitude sensor. So this is miniature class category. We had an evolution in our sensors right from Mark 1 onwards down to Mark 2, Mark 3, and in intermediate time we developed this microstar sensor. After then Mark 4 for very high precise pointing as well. So for this one, microstar sensor is the one which is used. Essentially, this has got an optics module with a baffle. Sorry, an optic sitting here with the miniaturized baffle, and then a CMOS detector with the necessary processing electronics, and it is an FPGA based processing system. And essentially this is the one which gives, as I told earlier, attitude for every nominal orbit to keep the satellite intact in its orientation. And for every burn, this has assisted the satellite in a very precise way, and then keep updating this inertial systems also in time. So we have seen that this has performed, based on this update, gyro systems could attain an accuracy of around 36 arc seconds, as well as attitude knowledge we could get within 32 arc seconds. This is what is happened in real time. And this graph predicts how it has behaved during the power descent phase. This is because star sensor updates are given in terms of quaternions. So we have expressed this graph in terms of that one, how it has happened for all the three axes, especially that yaw, roll and pitch axis, how this behavior has come, and very clearly predictable how it has settled on upon touchdown. The next important sensor is this laser based altimeter, which we call as LASA. This is also an absolute category of sensor meant for range sensing. We can't say it absolute because I'm sorry, because it needs, though it gives an update, but eventually, this has to be in the loop to give that velocity update. It has to take from inertial sensor. So it gives a range. Once it goes into NGC loop, then it can be computed, and then this measures line of sight. And the principle is, basically once a gated pulse take a round trip distance, we know that clearly, that C into T is what is the range. So, but it's a double pass, so we have to divide by the factor 2, and then this this was assisted with the commercial instrument. Basically, a pulse laser at erbium glass 1534 nanometer laser was used for this, and we developed electronics based on constant fraction discriminator logic, and then with the appropriate gating for this, and then we could clearly do all the ground-based tests, calibrate. The ground-based calibration, of course, I have not bought here, but this is the real time what has happened from that right from that 18 kilometer down to touch till touchdown, and this is the specific one during power descent phase. As you can see here, that LASA line of sight, as from the expected navigation thing, how closely it matches. This is captured in this particular graph, and this shows the difference between these two. And of course, this has some DEM errors inbuilt in this, which is acceptable for us. So this is one very important sensor which we have qualified, and it is going to go a long way. Even for our future space docking experiment, this is going to be in an improved version of that called a laser rangefinder, what we are developing now. And then we had this lander horizontal velocity camera. So this is a vision sensor, and then basically it gives, mainly it requests give an update at hovering phase. The principle is based on the Fourier transform principle only, wherein you have two frames separated by a distance means in the other domain it will be like a phase factor coming into picture. This is what is exploited in this particular technology, and then it is called image registration followed by a phase correlation. That means we take an FFT of that entire pixel set, and then see that once we do an IFFT, inverse Fourier transform, then we get a peak correlation. That means you will see a peak which clearly says about how that image matching is done, and then once we have the phase factor, from that we can get this particular pixel shift and then give it for NGC to give that velocity update. That's how it works. The main advantage is since it's a vision based sensor, it doesn't ask for any major demand in terms of power and mass. And also we had this heritage from Chandrayaan-2. So these are the performance parameters of this particular one. So it has got a reasonably good accuracy of around 0.3 meter at 3 kilometers height, and once it comes down, our processing is much smoother to give a better accuracy. And these are the calibration tests which we have done with helicopters. And then the one important facility at NSTL, which is a DRDO lab. You know, this is very important for our calibration, which was done at Visakhapatnam. So wherein we could ensure that accuracy of around 0.01 meters per second could be attained with this particular sensor. So this is how it has worked. It can also switch over to image mode when we were transiting. So it has taken some pictures of moon even before reaching from 14,000 kilometers itself. We started getting some pictures of this, and it can be operated in velocity mode, as I told earlier. And during which we have demonstrated, it can go up to 0.08 pixel. This is what is seen in real time, though the specification of around 0.2 pixel was there. So during power descent, we have seen that it has given an update right from 31 kilometers down to 20 meters also. So this velocity range was around 1600 meters down to 0.01, and then update to NGC happened at the right time. That 150 meters update during that hovering phase was very crucial, which led to the correction of velocity both in the north as well as east axis, to around 0.41 meters per second. As otherwise we would have faced a real glitch. Error would have 1 meter per second in these two axes, and another 1.3 meter would have crept in, and we would have had some small glitch. At least it would have led to some kind of a hard landing. So essentially, this is where this is nicely captured here. As you see here, navigation velocity versus this LHVC velocity. This is where that update, transition of update has happened exactly at that time to correct that velocity. And even in the real-time STK, you would have seen that there was a small retargeting type of thing. So that is a correction implemented by LHVC. So that led to this major success of our this Chandrayaan-3 landing.
It was all not manual intervention, right?
No, this is it's in autonomous mode, so it has to happen in that fashion. At that time, we can't command, and then within that time frame we cannot do anything. So everything runs in an autonomous mode. Yeah, that's important. That's why we build all redundancies, and then that NGC loop runs in such a way that if there is no consistency, then the other sensor will come into picture. That's how it is.
But how he finds out, okay, there is some bit or other thing is there, that is FFT, what you said, the camera, it will take the picture.
That looks for only feature. That pit and other things I'll come back. There is one more LH DAC. I'll explain in a very detailed way. So the another sensor is, hope I am not running out of my time, this laser Doppler velocimeter. So this works on the principle of the Doppler effect basically. Light scattered or reflected from a moving object experiences a Doppler shift in frequency, and this shift in frequency is a measure of velocity. So we will come to know from the previous frame to this frame what is the incremental velocity. So that is the advantage of this sensor, and this is an absolute sensor here, okay, for giving all the 3-axis velocity update. And we could not do this for Chandrayaan-2 time. We had some learnings in this at that time. So one is related to this erbium doped fiber amplifier, which is a very important development which we have done, because a 10 milliwatt laser has been amplified to 5 watts of power in a 3-stage amplification process, which is all done in a fiber optics domain. And this has taken its own time. So that's why Chandrayaan-2 time we could not develop this. And also there were noise levels which were very high. To develop that low noise, high gain and high bandwidth kind of electronics based on that balanced photo detector took us more time. And also it's important that we need to understand the polarity of velocity also. That was not done during that time. So polarity means whether it will be positive or negative velocity. That is also very important. So that is done by injecting a carrier frequency both in plus and minus 1 megahertz we gave to ensure that how to get these particular positive and negative values of velocity. So this was done during this time frame, and also our ingenuity in developing this processing electronics for laser drivers as well as TECs also were done during this time frame. And also we had this first we initially attempted with the monostatic type of optics, and we had a lot of glitch in getting the return signal. So we are dealing with some picowatts of this one. So what we have done is to enhance that one, we reduced the size of collimators and went in bistatic mode. That means our transmitting and receiving optics will be different, but they are adjacent to each other as is captured here. You can see here each one, all the three will have a dual type of head. So, and these are the calibrations which were done on ground at NSTL, essentially all the 3-axis velocity for the desired transition from that power descent phase to hovering at both the 800 meters as well as down to 150 meters.
NSTL is having some instrument there?
Yeah, they have a carriage which precisely translates over a distance, and it's a calibrated instrument there.
Okay.
So they have their own this one. Yeah, for their missile movement and other things. It's a DRDO lab, so which is used for this purpose. NSTL. Most of the instruments which had this kind of velocity measurement were done there only. And this is the thing which we have done for both ICT as well as IHT type of test, where we got confidence that exactly the way it has to happen, it has happened in these cases. And the calibration at NSDL has shown that we can even reach around millimeter per second type of accuracies, millimeters per nearly 10 millimeters per second, and all at a smaller value, smaller altitude. Yeah. To that level of accuracy we could bring down. And we have also tested during IHT that this particular sensor has updated NGC in a closed loop condition. So this was very important test which we have carried out in IHT. And then on board what we have seen is we had both the channels as soon as we enabled
got muted or something. We're not able to.
Yeah, it's got
hear.
muted. For the online audience, it's not audible. It's got muted. I will make sure that it is enabled again.
Again muted.
Yeah, again muted. Can you all please unmute? Yes, please go ahead. Yes, please go.
Is there anything like that in this? No.
No, now we can hear. Please go ahead.
Okay. You can get my audio now.
We
Yes,
can
sir.
hear
Yes,
you
sir.
now.
Please, sir. Yes, sir. Yes,
Okay,
sir.
okay.
In
Yes,
between,
sir.
it
Go
got
ahead,
cut
sir.
for a minute.
So what we have plotted here is this LDV velocity in comparison to LIRAP as well as propagated navigation velocity, which closely follows that numbers what we have for these two channels. But channel C, there was absolutely no update. But what has happened in our NGC, because of some time constraints, we didn't take only 2-axis update. Though we contemplated, already things were already tested and then qualified. So they didn't want to take the 2-axis update. So they went for that redundant sensor which was there. Obviously, in this case, it is LHVC. So even though it has given output, and even when it has touched lunar surface, we got that exact 0 velocity update. But then it could not be effectively used. But this is a good learning for us that how in future we have to build redundancy both in terms of in the sensor to have one more additional axis, as well as in NGC, we have to keep in loop even if it is some 2-axis update, which will be essentially useful for future mission. X, Y, and Z. No?
Okay.
That's how it is. So 2 axis it has come, but the other one is completely cut off. Reason we are exploring could have been some kind of a single point failure, either a fiber snap or a collimator disturbance or one such thing. But there were some health monitors which clearly indicate in the transmitter chain there is absolutely no problem. But maybe receiver line something is completely cut off. So this is one other important sensor which came into picture at 150-meter high. This was developed by SAC, called this lander hazard detection and avoidance. This is once again a vision-based camera, and this comes under the category of terrain-related navigation. There are some things which will be real-time. This is like you have some map of moon already stored, and then you take a picture in real time and then try to correlate whether you are there. So that's what is the principle what is used here.
Like a searching.
Yeah. But if image features match, then then immediately you come to know. So the processing time is very, very critical here. In real time, it has to update, and it runs in an autonomous mode. So, but what is kept is they kept on cold redundant for this sensor also. Like means one more sensor chain was there. The sensor head was there. Electronics is common. But in the event that also doesn't do, then eventually they'll transit to one 2D mode. From 3D mode, it will go to 2D mode. That means it will take a frame. It will just see what are the hazard points like what you get here. And then that will be the final update given. But it didn't switch over to 2D mode. We got in 3D mode itself. This was worked nicely. And then we could, really see that where we wanted to land, we have almost landed, but the numbers are yet to be assessed now.
How many data it has to compare? Like, okay, so many frames you have taken.
Yeah, the time given.
You are the right.
Correct. The processing time given for them is around 8 seconds. So overall time given for them is around 21 or 22 seconds, within which they have to assess this.
That the computer there.
Yeah. So these are the parameters which we have put for this LH DAC, and it has matched to the requirements. I had this small this one. Can we run this animation, because it will be more appropriate at this point of time? Possibly, I don't know if I go. Yeah, it happens. So this is how
But with this kind of sand or this one, it will affect that particular camera imaging also.
Yeah, that's why below 10 meters we were not expecting any update from anything. So it is the inertial sensors which will give the final update. It is going to be a free fall from there. The velocities were decided much earlier how much it has to be. From then on we decided. But based on the records of data, we have seen that we have got up to 4 meters also, 4 to 5 meters update with certain sensors. Like Kara and LASA has given update, even up to that level.
But another important is your thruster model and this velocity. How they are.
That is what it runs in that NGC loop, which will give a feedback and then control that engine. Yes. It has to be.
Those thruster motors also equally capable of doing the thing.
Yes. Those chain is clearly built that how it has to control.
So you will velocity will be at that point.
Yes.
Then what is depicted by your.
Exactly. That is the thing. So this is the deployment of a rover. Of course, we had a simulation earlier, and then how in real time. It happened on the early morning of 24th. 23rd evening we had landing. So around morning 1 o'clock, this deployment also was successful. And then rover could, first you could have seen that ramp deployment followed by a solar panel opening, and then rover coming down. And then it went through a distance of around 4 meters, and then in place rotation also has been demonstrated in this particular. This is all real time. Hope I can take another 10 minutes or so.
We are ready.
So this is the one in our STK which confirmed that we had a safe landing. So both the velocities, horizontal as well as vertical, and altitude, all are being zeros. And as per the program, this will say that once touchdown sensor is the one which will confirm there, and we had one leg touchdown, and then followed by that other 3 legs coming into picture, and our accelerometer has shown that there is a small, little one kind of a small, in the sense it had one more kind of a jump, small jump, and then settled, not to that extent of very high, but within that.
Only one leg is touched.
Initially one leg, and then followed by 3 legs. After then that first leg again slightly lifted, and then settled the first 2 legs or something.
That was okay. Plan was there. Okay.
It was there. Cutoff was given only if really if it exceeds something, then. But we don't have any control. If it topples, it is over. There ends the story. But then that is where the inclination with respect to that slope also is an important measurement with the LH deck. Okay. Yeah. So that has taken, and as soon as it landed, we had one more instrument called inclinometer. So that measured the tilt around minus 6.6 degree. In one axis it was minus 6.6, other one was close to around 0.4 or 0.5, like that it was there. So that was the tilt which was seen in that.
That is the tilt on the
lunar surface with respect to lander frame, yeah. No, ma'am. Actually, what see the sensor what is kept there, it is that touchdown is based on contact mode. That means 2 strips are separated by around a few 7 mm or so. So it has to come into contact. So we didn't give any cushioning type of thing. It has to.
It is like a contact surface.
Yeah.
Velocity zero. That is
yeah. That's all.
Another is a contact also.
Yeah.
But you said that properly everything is gone.
Yeah. But it won't. That's where. That's why when we had 2 hovering phases, 150 and as well as 800 and 150. After 150, we are ensuring that our lander exactly goes matching to that slope. But there may be some small differences which are within acceptable limits. This is what has happened, and it's a natural process of balancing that will happen when one leg touches, other one will have.
So, did you really find that initial target was not okay?
No, that didn't happen. Actually, in the first hovering, first target itself, we could land. We could successfully. That was anyway built on that, but it didn't use that second retargeting was not done.
The inner area for the 4 legs is like what, 1 meter by 1 meter? How big is it?
Dimensions of that lander.
Lander is around roughly around 1 meter, 1.5 meter. So once rover was successfully deployed, we had some specialized instrument. One such is this navigation camera, which was developed by us. So we had this stereo vision cameras, 2 heads, as you can see here, and then this right and left cameras will take picture of moon, and then based on this we can create a DEM. Of course, this DEM was done by SAC. We gave this particular thing, and we also at a later point of time developed that. And then I think these are the best high resolution pictures of moon so far what has been taken. So available today. So navigation camera proved to be very good, and it also aided in rover path planning. When it moved, this is the one which will say this is an hazard, you don't move this way and all like that. Path planning was given by. After landing, immediately we moved around 4 meters or so, but overall movement is around 103 meters we have gone. So these are the pictures. Once it has moved here, then we turned and then took the picture of lander also. That is what is captured here.
It does not come back, right? There is no return to the return.
Return, we can come near, but we cannot be again getting inside the lander. Such a thing is not there. But one more important test, anyway, I'll come back in that later slide. And additionally, we had the scientific payloads in rover. 2 such important payloads. Of course, I'm not talking about, there are other payloads also, it will take more time, which are done by PRL and SPL of VSSC. This is a very important device, MEMS-based device called Instrument for Lunar Seismic Activity. It's a seismometer basically. And then the main aim of this instrument is to measure moonquakes. So for that, we had a MEMS-based package which has been developed at LEOS, and we had two parts of this. One is meant for coarse range, as well as other one for finer range. Basically, it involves silicon micro machining and the technologies of anodic bonding, and then the standards of photolithography, what has been done in this. So essentially, it works on the principle of spring mass type of thing. If there is a cantilever, the deflection will introduce a capacitance change, and then that can be converted for useful purpose, like what we want, either into velocity or current. Okay. So this is what is done in this, and then this is the that MEMS chip what we have developed for fine sensor and coarse sensor. And this clearly says, we have gone up to a depth of around 150 microns or something, no? Roughly around 150 microns, this comb structure. We have one like a fixed electrode, other one will become like a movable electrode. That's how the deflection happens. And then capacitance change will happen, and it goes through an electronic circuit. We also have this direct converters also, which were used. And also for fine sensor, we used some discrete components to do this analog to digital conversion and then get this. So essentially, it is packaged in an HMC because of this reason. And this one proved to be a really useful instrument. Though on ground, we could not calibrate to better than some 100 nano G per root hertz. On board, we have seen a wonderful performance of this. So this particular instrument was switched on even before landing, much before landing, during transit phases also. Whenever we had some kind of maneuver, those events also were captured. For instance, you see, one of these earthbound maneuvers or lunar-bound maneuvers is what is captured here, where that wheel mode operation has happened. And then here is what we have initial control mode. And then we had this forward rotation, reverse rotation. In between, we have the burn. Then we do an earthbound maneuver or something. So this is procedure what is followed. We have to go through this forward rotation and then burn, and then followed by reverse rotation, and then comes back to wheel mode again. So this is nicely captured. Whatever you are seeing, that peaks are the instances which really, when the start of that one has happened, this has captured that disturbance. And by taking a moving average of the same, we could see that noise also is reduced, and then we could see a wonderful performance of this particular instrument, where the noise levels have come down less than about 10 nano G. So that is the level we could do. And incidentally, we had some capture of this particular whenever that rover navigation has started, that instant also has captured. And this is one event, a natural event which has happened in moon. We don't know whether it is a meteorite interaction or it's a moonquake. Only one event we could capture within that 14 days of time. One more important instrument is this laser induced breakdown spectroscopy. So this was also developed at LEOS. So this is basically meant for studying that elemental things present on the moon surface. It is a emission based spectroscopy. So what essentially it does is a laser beam of certain energy of this order, like it's a 3 millijoule, but when the power density comes into picture, it was 6 gigahertz per centimeter square. Essentially, when it touches that lunar soil, it creates a ablation there. So a plasma is created, and each element has got a characteristic emission, which in the return path is captured by appropriate optics there. So a collection optic, focusing optics, as well as collection optics also is there in that. And we have also, in this process of this development, we have used some commercial components like this holographic gratings, which are required for this spectroscopy, and we have upscreened and then used them. So, and a very extensive calibration based on lunar soil simulants have been done on ground.
How very, very important.
Yeah. So these are available. Some were provided by NASA based on earlier capture, and also we have some identified sites within our country, unearthed site type of soils which has a replica of this lunar thing. So those things were prepared and then calibrated with that. So nearly around close to around 72 samples were tested for this, and then that calibration was validated, and then eventually this is what we captured on the moon. These are the elements present already. We have confirmed this. Yes. These compounds of iron, titanium, sulfur is very abundant there, and also chromium, calcium presence was seen. Silicon also was there.
But how the distribution will look like? Okay, there is a big surface area here.
Yeah. We are capturing a small point. Actually, we should take a, we are supposed to move a very long. If you have to really account for abundance, we have to move for a longer distance and do that. Yeah. It is a grating which will try to sweep and then get. Yeah. Correct.
But is it possible to do it commercially, like for industry, we can use it? This
Yes. There is a feasibility of doing it, and it is being contemplated as well. But only thing is they wanted a miniaturized version. As of now, it is around 1.13 kg. They wanted less than around 0.5 kg or 0.3 kg type of thing. So which will be very useful for our own farmers for soil studies and other things. It will be really good.
Even for material also we can do it.
Yeah, we can do it. But this is a surface level emission. It's the only catch.
No effect of a aperture things like the moon is not a very smooth. It is the way we are.
Correct.
That also no effect will be there.
No, that's why this depth of focus, if you see, it has around to working distance can be 200 mm type of thing.
But it's penetrating.
Yes. No, penetration is very less only.
Okay.
But our optics can capture, if there is a variation also. That means it doesn't see any difference if it is 200 mm also. That way we have kept the depth of focus to be very large. So it doesn't.
So as you said, few difference was it could make it proper. So as it is moving, there is a.
No. The topple is for lander. This is a rover.
In the depth, it cannot find out. Okay, in the surface bar, it is different. In the depth, it will be different. So
no, penetration depth is very, very less for this. That's why other instruments like Chaste and all, they have done a drilling and then taken some samples also. Like that's how those scientific. Of course, I have not got some data of that, but those were also done, and they are in line with this kind of elements being present. So one more additional test, what we intended to do was this hop test. This is essentially done to ensure that in future, if you want to have some kind of a sample return program, which is planned in the future lunar thing, we need to lift off the lander and then see that we are able to maneuver that further. So it was lifted for about 0.3 meter high and then moved around 0.4 meter. So that was successful. So that's how this is captured. That earlier the trail of this particular rover, and then this particular it has come out of that lander impression. What it has got on lunar soil, that is what is captured here. You can see that trail difference, and then it has moved through a distance from that earlier lander position. So this was successfully done. Of course, one video also is there in our website. One can also access. It is available for public domain. So it shows only a small disturbance type of thing, a soil disturbance, and then coming out of that. But essentially, this is a very useful one which was done. Next 5 or 10 minutes, if you give me, I can capture some of the things about Adithya. If you feel it's okay, I can continue.
Please continue, sir.
Yeah. So soon after this Chandrayaan success, hardly within 10 days, we were, as per our plan, we have to get into Adithya mission. So Adithya is mainly to study about solar related thing, and then this was planned for Lagrangian 1 orbit. So essentially this is done because we won't have any disturbance if it is placed in the L1 orbit, and any Lagrangian has its inherent advantage of being a very stable orbit. That is the reason why we went for this L1 orbit. And there were about 7 payloads, scientific payloads, which were gone along with the Adithya L1. And this one shows about how this Lagrangian distribution happens. Of course, L2 being a very stable orbit, but it cannot continuously see without any eclipses, whereas L1 has got an advantage, though little unstable compared to L2. But this is what is preferred by us. And if you look at the
What is actually L1? There is no gravity there.
it will be balanced between Earth and Sun. That's how it is. So it will be like a stable thing. The gravity acting between the Sun and Earth for that particular object there will be quite balanced there.
It is still in the orbit.
No, it has not yet reached. It will be going. This requires a lot of maneuvers like what we have done here. Of course, most of the maneuvers are complete. If at all a correction has to be done, it will be done during November end. And then once we reach that AOP of January time, then we may have to look for that halo orbit injection. So that is one crucial phase there. So halo orbit, it will orbit for nearly 180 days in that. So that's a very tricky orbit. What is captured here? So we have to really see how well we can go into this. First time we are going to do this. So essentially, this is meant to study the different layers of sun and the sun-related solar activities, how it happens. So solar wind, and then the coronal mass ejections, and then solar flares, and then also some what they call coronal loops. Essentially, all these payloads are oriented for that study. So these were the payloads: Visible Emission Line Coronagraph, which was developed by IAA, for which optics we have done. I'll capture the type of optics which we have done for this particular VELC. And HELIOS is a high energy orbiting X-ray spectrometer. And SUIT is a Solar Ultraviolet Imaging Telescope. And it is expected all that solar disturbances, much of these things happens between 200 to 400 nanometers. That is the reason why we wanted to study the solar disk using this particular telescope. And SOLEX is a low energy X-ray spectrometer. Aspects, it's an Adithya solar wind particle experiment. These were developed at different centers, and PAPA is a plasma analyzer package for Adithya. As I explained earlier, these are the objectives what we kept: coronal heating, solar wind, coronal mass ejection layers, dynamics of solar atmosphere, as well as wind distribution and its temperature. So I'll come to this major instrument which is there in Adithya. This is that Visible Emission Line Coronagraph. As you can see, the type of optics, how it is distributed. First time we have not done a kind of usual telescopic structure. This is a benchtop type of thing which is qualified for space use. So, but it called for very big challenges in terms of the optical requirements. Essentially, this coronagraph does the image of solar corona, and also has got spectroscopic studies at this specific channels, which I am not able to read, maybe around 530, 789, as well as 1074 nanometers. So in all this, and then a continuum channel at 500 nanometers. So this is what is going to be done by this, and for which this particular M1 mirror, which is the prime mirror for this thing, has to be having a very low roughness of the order of an angstrom. So this was demanded by them for the entire surface of around, roughly around 200 mm this is. So it has to be within, 1 angstrom's surface roughness. So this was a real challenge, and we have to develop certain polishing technologies. This was done on a zero-dur base material. Inherently, being a glass ceramic, it is very difficult to achieve very high accuracies. What is reported in literature itself is of the order of very small samples of around 25 mm. One can reach around 1.2, close to 1 like that. But we could attain around roughly around 0.8 to 1 angstroms. That is what is the measurement repeatability what we have seen. But they demanded for different spatial scales also. This was around for a 10 micron by 10 micron strip, that was the number, and taken at several places. We had about nearly 36 measurements on that different locations of the mirror, as well as spatial scales different means up to going for 1 mm also. That objective what is used will have a spot size of bigger number there. So over that we have seen around 2.5 angstroms, and once you extend up to 2.2 mm or so, that spatial width of that particular beam, then we have seen around nearly close to 4.2 angstroms. This is the number what we have achieved.
How do you measure it that okay, this nanometer, what is the instrument you are using?
This is in angstroms. There are some instruments like white light interferometry based thing, profilometers, which works on optical interferometry principles. Yeah, that is the one which is comes to this particular one. AFM also can do. Definitely AFM can do. In fact, AFM has got a better resolution, but the only disadvantage of AFM is we cannot measure on the actual optics. We can, on a sample, we can measure flat samples. On the actual, this is a off-axis parabola. So whereas white light interferometry, has that manipulator over that, so that it can go and then measure on the actual surface. Yeah, exactly. That's the thing. So these are the assemblies which were realized. We had a variety of optics. One is this zero-dot based low roughness mirror, and coating is a very important aspect here. You may achieve a polished surface, but upon coating it may get degraded. So for that also we developed some special processes, how to clean this and then get this coating without any spatter over the 200 mm. Yeah, basically it undergoes a full level mechanical analysis, FEM based thing, and then in the actual thing itself we'll develop a model and then subject for that kind of vibrations and temperature escalations. So it undergoes all the endurance test, and then we ensure that no disturbance happens in the optical alignment. And we also had a stainless steel mirror. No, this had some kind of elliptical hole drilled on this, and then still this surface figure has to be retained. It's a real challenge for this one. And then we also had a silicon carbide mirror just to throw that central disk, because this is an internally occulted system where that solar disk has to be thrown out, and only we use the corona to do that subsequent studies. So internally occulted systems. So we made a silicon carbide mirror also with the help of ARCI. We got that CVD coating done on that sintered silicon carbide, and then essentially developed a polishing recipe to get this mirror to very low roughness. Yes, it's a very difficult technology. Even today we have, for larger sizes, we face problem.
Is it a vapor deposition technique? Or
yeah, chemical vapor deposition technique. So that is the most stable. We are also exploring some alternate ways of doing it. But for very larger sizes, challenges still remain. Going above 0.2 meter. No, the reason is inherently what happens is that material mismatch also creates a problem. Suppose we go for some other coating. CVD is a silicon carbide coating over silicon carbide, so it has a very good match. If you go for alternate layers, there are some instabilities.
But it takes a lot of time to do.
Yeah. Time is one factor. The yield also is very poor. So out of some 20 blanks, you may get 1 or 2 blanks, and each run costs around 10 lakhs type of thing. One coating run is around that. And this is another off-axis mirror, which is a zero-dot based for M4, and a variety of lens assemblies which are used in this. Everything is accounted here, and everything we have developed as a assembly this time, and then given so that they can directly integrate into that bench. And then what challenge we faced in M1, much more than that we faced in this litro assembly. The reason being, this is also roughly around these are Japanese glasses what we have used, and as per our mechanical design, initially what we have seen is it should be able to withstand, but when we subjected to this endurance test, it cracked and then came off. Like, so we have to revisit all this, and then this took a lot of time for development, and then we could successfully qualify finally with with a lot of reinforcements within that assembly for each lens, and then subsequently stacking them in that assembly. So a lot of things have been done. So this is a technology which we are yet to publish, but it may come very soon. Yeah, all are standard ARC coatings only for lenses. So coating wise, anyway, we have larger chambers and better stability in terms of its deposition rate as well as uniformity.
But any other kind of test is also the only centers test. Like, okay, space, there's a lot of particles are impacting on this plastic. So any other kind of test also you do?
In terms of this is not expected in this. Correct. It is true, but we have not gone for such type of tests. Only our temperature escalations as well as extreme temperatures, storage as well as for cycling, and then followed by vibration with a margin. Of course, future Gaganyaan and all, they are asking what you are telling, like if it has some micrometeorite type of interaction, how we have to encounter. Those tests are to be contemplated for future. And one more development is this solar ultraviolet, for which optics also has been developed. Here again, we had challenges related to individual mounts of this mirror. When we put inside, once again, kind of heavy distortion happened, and then we have to revisit all this mounting schemes, and then subsequently corrected and got this done. Of course, this was as a payload, it was developed by Ayuka Pune, and then this was the last deliverable for our Adithya 1, because we faced some issues related to filters also. So there again, that mounting, because this being a very thin filter, they have got around 100 mm with the 1.5 mm kind of thickness. So any mechanical mount will inherently distort that. And then once it undergoes a test, it used to develop a lot of problems with the optics. So carefully we have evolved a scheme and then did this mounting, and then finally we made it a success. So these are the things which I wanted to capture. Essentially, I wanted to say at the end, LEOS has got, I could say that it's a hub of, not only for developing high accuracy sensors. We had an evolution in each of these sensors to have a better performance. As I was telling about only star sensor, we also had a sensor called high accuracy active pixel sensing, this one, which I could not get a slide now, but essentially, that has for Adithya, it has seen on board 4 hour-second sensing, sun sensing. So this is one of the beauties which have been done at LEOS. And we also have a very established lab for doing precision optics. We can go up to meter scale, like 1.5 meters is something which we can contemplate, and lightweight the mirrors up to 80% to 85% we can really do. And also instruments which are based on this photonic based developments, like plenty of MEMS based devices, fiber optic instruments, laser instruments, MEMS devices, and detectors, special purpose detectors also were done. So thanks to IAC for being behind all these things, plenty of technologies where exchanges have happened, and Professor Navkant Bhatt knows very clearly how much of things have happened earlier, and we would like to have more and more collaboration with IAC and like-minded institutions to go further and further. Thank you so much for your attention. There are any other?
Thank you, Dr. Sriram. In the interest of time, I would ask the online people to ask questions if they have, because offline people can take it during the tea break.
Right.
Sir, good evening, sir. Myself, Dr. Santanam, DRDL Hyderabad, sir.
Okay.
Yeah, I have one fundamental doubt, sir. This a lot of instruments you have used both in Moon mission and Adithya, particularly Moon mission. There are some uncertainties will be there in each instrument, right, sir? whatever the uncertainties you have considered while you are doing testing in Earth and in Moon, you have to consider some different uncertainty values in the instrument, the measured parameters basically for variety of instruments.
Yeah, you're right. See, what happens is the condition is basically, essentially you have a exposure which is very different, as well as it is in a vacuum. These are the things which we have to generate in this, for which we do this testing, specialized testing, in situ testing in thermovac. This is also done for almost all the sensors. And also I was mentioning that there are certain facilities within India which has been used. We didn't go anywhere outside for this, except for buying some of these components, which essentially everybody has to depend on today in India for all these electronics as well as raw materials. Yes. Barring that, I think every other test has been done within India, and then we could do it. Lab-based test, outside, field tests. Additionally, this kind of endurance test and the real-time situation tests on board what it is going to see. All those are done and then recorded, and we have kept margins in each of the sensors to ensure that on board we won't see any discrepancy. Does it answer your question?
Yeah. Means basically, how did you arrive those uncertain numbers? Basically, just specific question I'll ask. One
actual measurements. Some are based on simulations, but sensors wise, everything is done. I was mentioning that helicopter test, and then we also had this crane test, and then lander drop test. Everything was done in real time.
On the moon, when you are, so for example, sir, I heard just
on the moon also during transit phase also we have switched on and then seen some of the performances even before the actuals have to commence.
For example, thermal gradient around some 8 mm or 8 cm, something like that.
Yes. There are monitoring health monitoring things which we have been keeping keeping a watch on that, and then ensure that all the systems are maintained within the stipulated numbers. So nowhere we have seen that it has crossed any limit, and every sensor which is instrument or this one which needs to be protected and then exposed only to lunar atmosphere also is done. Essentially, that warm electronics box is one for Rover where all the science instruments were clearly protected and kept.
Protection is one thing, sir. That how will you arrive at uncertain numbers which you are done in moon, Earth and in moon? Can you say that is the correct number? Like, how can we conclude, or just curiosity only? Nothing.
The evidence is what numbers we have arrived at on Earth, and the simulated numbers or the tested numbers in vacuum. Sir, we have got a better number in lunar region. That's what essentially has converged. Okay. What is evidenced is the numbers are what these sensors have given on board is a number better than what has been arrived at on ground.
Okay.
And in the interest of time, can we take the other question? Anybody
please,
else?
Please. Thank you. Thank you.
Sir, I'm Natarajan here. Can we use silicon carbide single crystals instead of the sintered silicon carbide?
We can definitely use, sir, but we need a larger area. That is the whole catch of this particular development.
What the size?
This typically what we have used here is around 40 mm size.
I think it is possible. Now we have the technology in DRDO and we have developed it.
40 mm can be used for instance, if you have to use for regular optical telescopes, we need not less than 0.5 meter type of thing. Now 0.2 meters or 0.5 meters are very common. So that is where I think we need to definitely have some alternate technology. Of course, crystals can be used for certain purposes. I am not denying that.
Right.
Trial. Anybody else?
I think Veda, in the interest of time, maybe we can close the session.
Yes. I would request Professor Naukanbhat to hand over the memento on behalf of IEEE.
You can write to me to my mail ID, or you can message me through WhatsApp. I can be, if I can really, it will be, I'll also encourage that.
That's very nice of you to offer that.
Trial.
Demonstrates the kind of technological power India has.
Trial.
I mean, ISRO has done an amazing thing both back to back, Chandrayaan and Adithya, and the contribution by
I think somebody wants to.
yeah. So it just shows the kind of precision engineering.
Just amazing, exploiting light and fooling the photons and trying to harvest the best out of it, right? And this is amazing, and your talk it has opened up the kind of possibilities. Thank you very much, and on behalf of IEEE, there is a small memento I would like to
Thank you so much, sir.
Thank you.
It's my pleasure to be, part of this particular.
Very interesting. Don't stop it. It was a good movie.
Thanks,
Okay.
Giri, for
Ma-
enabling.
no, no, I should.
We should thank Giridhar for.
No, I think more than the stipulated time. I think I ran over double.
No, but we had a lot of good questions. Yeah.
There are a lot of varieties of questions are there.
Yeah.
Never ending.
Maybe we can join for the
From
team.
mechanical, electronics,
Right. You need everything coming together, materials.
impact
Yeah.
mechanics,
Yeah.
and so many endurance, the fatigue, life assessment, so many things are there. And the calibration, another big area. Then how you certify is another area.
Correct.
Then uncertainty, how you take.
Yeah, please join for the team and continue.
Thank you all.
Thank you all who have attended online and offline. On behalf of IEEE, we will end. Thank you all and end this session. Thank you.
Thank you. Out of my domain.
Very nice professor. Like that.